All right, so we have our Unit 4 free response practice question. This one's from 1981, so again, we're going back in time. So things have changed slightly in the way some questions are phrased. Definitely the amount of calculus required has changed over the years. There's not as many calculus proofs needed anymore, and also you used to never be able to use a calculator, now you can. But this is still really applicable because this one allows us to focus on the free body diagrams. So we've got the block on an incline with a force acting on it in the horizontal direction. So it's not in the same direction as the incline, which always makes things a little more interesting. Okay, so let's take a look at the rubric for that. We're going to first draw a free body diagram. We're going to develop an expression in terms of m, theta, f, mu, and g for the block's acceleration up the plane. So great Newton's second law question. With no numbers. I know that's always a sticking point for a lot of people. Develop an expression for the magnitude of the force that will allow the block to slide up the plane at constant velocity, and what relation must theta and mu satisfy in order for the solution to be physically meaningful. So that is our question, all three parts. Okay, so let's take a look at this rubric. So first, our free body diagram. We have 4 different forces that we have to worry about, and something that you absolutely must have for free body diagrams in the AP exam. This rubric actually doesn't have all the details that later ones have, so I'm going to outline that here while we have a chance. First of all, any forces being drawn must originate at the center of the body and radiate outward. So you notice that we have that force that's pushing on the block. In the drawing they gave you, it's over here pushing into the block. You cannot do that on the free body diagram. It must originate at the center of the body and radiate outward. So that's why this force is here. Gravity is straight down. Normal force is perpendicular to the surface, and then friction acts opposite the direction of motion. If you labeled friction as lowercase f, that should be just fine. If you had f sub n up here, that's fine. If you have w down here or f sub w down here instead of mg, that's also fine. So notice they say any reasonable label is acceptable. If we can tell what you mean, we're good to go. Notice though, the components of the weight are not here. If you have the weight mg here, that's all you can have. If you were to add in the components, the mg cosine theta, the mg sine of theta here, and still have that weight, typically those will count for extra vectors that shouldn't be there, and those would yield points being subtracted. And because it was 2 extra vectors, it'd be 2 points lost. You can have the components if you do not have this overall resultant vector, and then that's fine. Okay, for part B, you have to start with Newton's second law or some nature of that. So always state sum of the forces equals ma, or F net equals ma, something to that extent. That's a point. Just stating that is a point. Just like stating energy is conserved is a point. Just like stating momentum is conserved is a point when the problem applies. Okay? Showing that the friction is equal to mu times the normal force is a point. Okay? Then you need to have your forces split up in the perpendicular direction and in the parallel direction. And so you could have said in the what was I going to say? Your perpendicular forces, your normal force is going to equal, oh, that's what I wanted to say. So in your perpendicular plane, the sum of the forces equals 0. So you could have said 0 equals the normal force minus mg cosine theta minus f sine theta, and then showed solving for the normal force that way. But ultimately you had to solve for the normal force, and that's a point. Then having your parallel forces, and that's going to equal m times a. So you could have said ma equals f cosine theta minus mg sine theta minus mu times the normal force. And then here you see they've solved for the acceleration. And so each term in that expression is a point. For part C then, when v is constant, remember that means our acceleration is 0, okay? So that means that the sum of the forces equals 0. So you can then plug back into your parallel equation where the acceleration in the parallel direction is 0. And then that allows you to solve for, to have a relationship between theta and mu. And so ultimately you're finding here that tangent theta must be less than 1 over mu for the velocity to be constant. Okay? So I hope that this was helpful and you got a little more insight. The big thing I wanted to focus on in this video was how to draw those free body diagrams, because I am 90% sure you're going to have a free body diagram on the AP exam.